So I'm starting to record my lecture number 2. I planned to do it much earlier. I planned to do it last week, but something happened. They caught me. You know that I have a kind of a long history of going to China, and the medics got me. So they put me in the coronavirus ward and they kept me in isolation in a special confinement, like a cage, glass cage, with this biochemical suits. They were actually supervising me for 4 days, and after finding nothing, they released me. So I'm home, and I'm recording for you my new class in functional analysis. Okay, so I'm very glad we can do it from home and not from confinement, hospital confinement. Therefore, let's start and let's continue, let's say, our topic. So let me recall. The course actually stopped in the middle of the introducing. I was just in the middle of introducing the weak topology on the Banach space E. So let me write the title, and the title is weak. Just a second, everything will be okay. So let me see. Pencil. Okay, weak topology. And we will denote this topology like this is topology on sigma stands induced topology. E stands for the Banach space E. E star is dual, so this will be the topology which is induced by all continuous functionals on E. So let me recall that actually, let's say, what we are talking about. Let E be a Banach space and we denote by, and let's write the symbol sigma E star, the smallest topology that makes all functionals F belonging to E star continuous. Let's say, so we denote maybe this topology also by the symbol and I put it like this, tau means topology and W means weak, by this topology, by this symbol. Okay, so in other words, the weak topology write it down, sigma E star, or I'm just writing down in other notation is W. If you want to be less precise, it will be TW, because that's T is topology, W means weak topology, induced on E by the family and this will be the family all the linear functionals on So it goes to R such that this F belongs to E star. So this is induced star. Maybe also this is convenient. For convenience, we will also write, and I put here a symbol that in red, so you can see this is introduced, this new symbol with W to indicate that the space E is considered together with the topology, the weak topology sigma E star. Sigma E star. Okay, this actually is nothing else than recalling the material that we already did in class. And of course, I should also indicate a couple of important things, mainly for a given point x naught belonging to E, we have the following basic neighborhoods. That means these neighborhoods form a basis of neighborhoods, and that means every open set can be created using this particular open set, unions of this particular open set. The following I put here: basic, maybe red, basic neighborhoods. Basic neighborhoods. And these neighborhoods are the following. So what they are, I will just simply put V stands for the open set, V. Then you have here F, this will be the finite set of functional, and epsilon will be a positive number, real number. So this will be defined as the set of all x's. Okay, write it down in E, such that for every f belonging to f, we have here f, and here is x minus x naught. Make it like that. One is smaller than epsilon, where f is contained in E star, is a finite set, and epsilon larger than 0 is just a real number. So this is basically done. Of course, notice that by the continuity, and that means if I say continuity, I don't say weak continuity. I say continuity means the strong topology, means the original topology on the Banach space. E, the sets, what continuity? I lost my thought. Of f belonging to E star, the sets V, F, epsilon are open in the strong means usual, the Banach space topology. Strong topology on E. So maybe I need to make it nicer. On E. So what? How to recognize? So what it makes different this strong topology from the weak topology? What are the differences? So that also can be explained. Of course, as we showed in our class, maybe I put here like this, observation, so that means remark. And this is kind of a simple exercise showing you that open balls in let's say that open balls in Rn with respect to the norm infinity actually is a weakly open neighborhood of 0. So let's say like this: if dimension of this Banach space E is finite dimensional, and we know that in this case this space can be identified with the Euclidean space, for example, equipped with the norm little dot infinity. So that means if this 10, I can write it down, E can be identified with Rn together with this norm infinity, you know what it is, and we can easily notice that the open ball, so put it like this, the open ball above 0 in Rn is nothing else than the neighborhood of f, and this is f, and this is equal to 1, epsilon is equal to 1, when f is equal, and this we have here, E1 star, E2 star, and this one is En star, where E star k on Ej is the Kroneker's delta Kj. So we actually prove this, and we indicate it. So that's a simple observation. Therefore, we have that the weak topology in this case is equal to the strong topology. So there is no difference between these two topologies. No difference. However, in the case the space is infinite dimensional, that's a big difference. That's a big difference. So let's formulate it. Let's formulate it as a lemma. Okay, call this lemma somehow. I think it's a good idea to give a number 1. I don't know, maybe I will use another number. So let E be a Banach space x0 is a point from this Banach space. Great. And consider I write it down, weak basic neighborhood consider weak basic neighborhood of x0, and then we say given by, maybe I don't need comma, given by, and I move a little down, and the formula is like this: V F epsilon, and we know what it is. This is a set of all x belonging to E, such that for every f belonging to f, we have here f, and this is x minus x naught smaller than epsilon. Put put L is equal intersection, and for every f belonging to kernel of what am I doing? To f kernel of f. Okay. 10. Clearly L is an infinite dimensional, then L is an infinite dimensional subspace of E, and what do we have? I have here that x naught plus L is contained in this V F epsilon. Interesting. These weak neighborhoods, they're all unbounded. They contain the subspaces, and not any subspaces. They contain big subspaces, infinite dimensional subspaces, like this, x naught plus L. Those open neighborhoods, those open sets in the weak topologies are really big, unbounded. That's kind of a surprising. So let's do the proof. And to just simplify the notation, I just put f is just simply equal to like a finite set, so the f1, f2, dot, and then you have here fn. We already know, so this is our L, and assume that x belongs to the x naught plus L. That means we have here that x is equal to x naught. Put here V, where, and I can write it down, f on V f k is equal to, again, make it not so nice. Fk V, Fk V is equal to 0, for k is equal 1, 2, and that's exactly because this is your this is your set F. Those are your elements from the set F, and for this elements, and we have here that point belongs to the kernel of Fk. If this belongs to the kernel, that's exactly this condition that it satisfies. Okay. So let me continue. So what do I get here? So that means, in particular, and we have. So I put it like this. Take this x, so what is the x? Put here like this, Fk x minus x naught, which is equal, okay, there is this x is written, this is your x. So I can write it down, that one is equal to Fk x minus, x naught plus V minus x naught. Do the cancellation, bang, and then you just simply add the line, and this is equal, and that is equal to Fk of V. And then look above here, and you can write it down. This is equal again, 0, and 0 is definitely smaller than epsilon, so this implies that x belongs to V F epsilon. And that's, of course, for every such x. So we have here that V F epsilon contains x naught plus L, and we proved this result. This is basically everything. So, so that's it. Maybe I should. Is this clear that L is infinite dimensional? Is this clear? Maybe remove these things. So, up to this moment, we don't have it. Now, notice that maybe I should add it. L is indeed infinite dimensional. Okay, notice that indeed. And then let me go down. And in such a case, let's say, okay, suppose, okay, I will not simply, I just simply write it down. Consider the map, the linear operator and I put here A that goes from E to Rn, and this linear operator is given by X is equal, so we have here F1 of X, F2 of X, those are the numbers, and this will be Fn n of X. And in such a case, since each of those those are continuous, so this one is continuous, means bounded. And if this is continuous, then we have here that first thing that then the first thing we have here that L cannot be equal to 0. L cannot be equal to 0. So that means this is actually a subspace. Then L cannot be equal to 0. Okay, if L cannot be equal to 0, then why? Because if L is equal to 0, since in such a case, since in such a case, we will have here that A goes from E to image of A, which is the subspace of a finite dimensional space, so this is definitely closed, would be isomorphism. It would be isomorphism. And that, of course, by the open mapping theorem, namely the inverse of A, because it's injective, maybe put it in red again, so this is actually injective, would imply that this is isomorphism. So if this is an isomorphism, that means E is finite dimensional. Okay, so we have this. So what about L is infinite dimensional? Okay, I think this is a good problem. You could definitely try to solve it by yourself, and assume that L is infinite dimensional, and find the basis in L, find the dual basis in L, and add this dual basis to the functionals f1, f2, fn, and you will get exactly the same argument that tells you that no, it is not possible, because if L is finite dimensional, you can construct a linear operator, similar way like A, except it will be like A, and then you will get here additional. So for example, basis like E1 star, En star from the subspace L, and this will give you again an isomorphism of E with the finite dimensional space. I will put this problem as an assignment problem. The remaining, so assignment, show that L is cannot be finite dimensional, is infinite, come on, why it is so ugly? Is infinite dimensional. Okay, this will be, it's okay. This will be added. Okay, we have it done. So we have several other things that were actually already called, and maybe I should indicate to you, so the proof is finished. So let me list this. Recall that we already proved the following fact. So first one, that the weak topology is Hausdorff. Very good. So we already know that the weak topology, so we also have here that the T is contained in the T in the regular topology, but if dimension of E is equal to infinity, then tau of E is contained, but it is not equal, cannot be equal to T. T, W, weak topology cannot be equal to W. And what else did we do? We also know that notice, okay, that maybe we should remark it. Notice that the basic neighborhoods and we call it like this V, and this is written like this F epsilon of a given point x naught are convex sets. So in such a case, that simply will mean that, put it here, that TW, or then means, okay, TW is a locally convex topological vector space. And finally, the remark is, also additional remark is that if dimension of E is equal to infinity, then the topology, the weak topology, T tau is not metrizable. And that, of course, you see, you should understand that that's not what we are proving. This is just a result, well-known result that we just refer, if you're interested, to the literature. So you should definitely look into it in the literature. So we understand that there is a big difference between weak topology and strong topology. They are not the same for infinite dimensional K spaces, and this is exactly the topology that is needed to study infinite dimensional spaces. infinite dimensional Banach spaces. So let me switch to the new paper because we finished this one, and let me continue. So we also introduced the notion of the convergence. So we have here like this, the weak convergence. I'll just simply say it. I'm not going to repeat the definition. Weak convergence of sequences. So in this case we showed, so we denote this one like this, xn is weakly convergent to x naught. So we'll write it down. That means the x sequence xn converges to x naught with respect to the weak topology. With respect to the weak topology. Yeah. You can write, okay, I write the finish. So if and only if, for every V belonging to the weak topology W, such that this one x naught belongs to V, there exists an N such that for every N larger equal 10, and we have here x n belongs to V. So that's basically the limit is unique. We mention it. In this case, we have that this is a Hausdorff topology, so your limit is unique. There is no problem with it. We also have this proposition. And in this proposition, let's say like this, let E be a Banach space, because we have to be precise, space, and xn be a sequence in the Banach space E, x naught a point from E. A. We have here that xn converges weakly to x naught if and only if for every f belonging to E star, we have here that f of x n converges to f of x naught. And this is basically the definition of the weak topology, because that's exactly what it means. And then we have here B. We have here if xn actually converges strongly to x naught, then this implies, but it's not the vice versa, that xn converges weakly to x naught. So please remember, you don't have the reverse. So that's not true. That's not true. And then you have here C. If xn is weakly convergent, then xn is bounded. Actually, you can find out that in such a case this will be limits. For example, limit supremum of the norms of xn will be like, okay, the existent is bounded. This is bounded, and then D. And then D, if you have here xn converges to x naught, and if fn converges strongly in the dual space to f naught, then we also have that fn xn converges to the f naught of x naught. And all these things were already discussed and were proved before. So this was already proved in the lecture. I'm repeating myself. I don't need to prove these things. And the only thing that we mentioned in the last class is the following theorem. Let E be a Banach space, maybe be a something happening. Sorry, just give me a second. Okay. An infinite dimensional Banach space and put. So I put here B, this is the closed unit ball, so this is X belonging to E, satisfying the condition that X is smaller equal than 1, and S, put it like that, this denotes the set of X belonging to E. Now that's again like a not nice. Dot such that X norm is equal to 1. I notice that if I try to accelerate my writing, it becomes messy. So that means I have to write slowly. I don't know, this is good or bad. So this is unit ball, closed unit ball, and this is unit sphere in the space E. So what happens in this case? What happens in such a case? We can write the conclusion 10, and this is only in the case of infinite dimensional space. Infinite dimensional space. This is very important for this statement. This is infinite dimensional. Then the closure, the weak closure of S is exactly B. So let me write it down using the symbols I, E, and I will be using the symbols, namely I will write it down. This is my S. I take the closure and I put here little w. As you notice, I'm using W to say weak, and this will be exactly equal to B. Exactly equal to B. Okay, let's do the proof. So we begin with the following. So notice, let's say like this. Notice that a point X belongs to the closure of this weak topology, if and only if, and this is just by the definition of the closure. By the definition of the closure, for every V F epsilon, and this is going to be weak. So basic neighborhood, basic weak neighborhood. This is basic weak neighborhood, basic weak neighborhood of X. So for such a neighborhood, we have here that V F epsilon intersection with S is not equal to the empty set. So that's the definition. Every neighborhood of this point X intersects the set that we are closing. Set that we are closing means S. That means S. Okay. So let's do it. So what can I do? So we already know that S is contained in S. That's also trivial property. So consider X belonging to E such that the norm of X is strictly smaller than 1. Okay, it is strictly smaller than 1. Very, very good. Okay, we need to show that X belongs to the closure. That means in such a case, what do? Let VF epsilon, here epsilon larger than 0, of course, epsilon larger than 0, okay, be a basic weak neighborhood of x. Make it x naught, x naught, x naught. I want this to be x naught. Take any of x naught. Okay, this one is also x naught, x naught, x naught. So one more time, I added here little index. I just want to make it like compatible with my lemma 1 that I proved. I proved lemma 1, okay? That's supposed to be useful. So, of course, I put here the same notation. Oh, this is all. Okay, so then of course, let's say like this, by lemma 1, by lemma 1, there exists a subspace, there exists a subspace L, which is different than zero subspace, such that x naught plus L is contained in V F epsilon. Okay, let's do it. So we have here, so this is my, let me write it down, make a picture. So this is the subspace, this is 0, this is my subspace L, and now I have here the unit ball. So let's say this is my unit ball, this is my space E, very good, and this point x naught is here, x naught is here, so that set x naught plus L, x naught plus L, wow, it's unbounded. This is like a line crossing through. Immediately, this is not a big deal to show just by looking what's happening. The points in L go to the infinity, so this is an unbounded set. What is inside in this ball B is bounded. And where is our S? S is here. The S is the boundary of this set. S is the boundary. So of course this set x naught plus L intersects. So put it like this, y naught. The y naught, it intersects the S. It's intersecting to S. So let's emphasize. So the set x naught plus L, because it's unbounded, it just goes through from x naught out to the infinity. It has to cross the S. Find a nice argument to justify it formally. You can justify formally everything. So let's write it down. Since I put here like y, there exists a y naught belonging to S, such that y naught belongs to x naught plus L, and I take the intersection with S, which is contained in x naught, not x naught, in V, and this is F epsilon intersection S. We have that. This intersection is non-empty, and that's exactly what is required here. This is the condition. This is this condition that we need to have to be satisfied. This is this condition. One more time. This condition. So x naught belongs to the closure, weak closure of it. Okay, and that because we chose the x naught arbitrary means that Where is my set? Oh, I lost everything. Oh, such that means that this ball is contained in the weak closure. So we got it. So the only thing now what we need to show is that, okay, we only need to show is that we need to show that since this one contains S, that the ball B is weakly closed. Okay, let's do it. So, for this purpose, seems like it. For this purpose, suppose I have here x naught that does not belong to B, and that means in fact that the norm of x naught is larger than 1, and we need to find a neighborhood, a weak basic is enough, neighborhood of x naught such that, did I write basic neighborhood? I need to, okay. V f epsilon of x naught such that, I have to be written very carefully, such that Vf epsilon intersection B is empty. So this is an empty name. Okay, let's do it. Okay. However, so maybe like this. However, no, I don't need to use however. What's happened? Oh, where is my stuff? Let me do undo what I did. Edit, undo. Oh, it came back. This technology is very surprising. You touch the button and everything disappears, and say, where is my lecture? Gone. And how do I get it back? Figure it out. Okay, so let's see. I have to be careful. I have a button here, button there. So difficult. So I need to construct it. However, okay, I use however because it was warning me. Don't. However, B is closed convex, and I put here A, I just take the point x naught is what it is, compact convex. So by Banach geometric version number 2 theorem, we have that there exists f belonging to E star. So let's go down. Of course, f is not equal to 0, such that let's write it such that, okay, for every x belonging to B, such that, okay, there exists an alpha belonging to R, such that we have this following property, that f applied on x is smaller than alpha, is smaller than, okay, fx naught. Fx naught. Wow, that is kind of interesting. So now if you look at this particular situation, then let me illustrate. So let me write it down. This is my real axis. So this is the real axis. Oh, goes very nicely. So this somehow here is the alpha. This is my alpha. So the b, all the points from b. So this is f of x. X belongs to b. Are here. So maybe let me change to red, and then we have here all these points are here on that side. And then we have here the point, and this point is f of x naught. So of course you can choose an epsilon sufficiently small, so this point here, f of x naught minus is epsilon, will be still larger than alpha, and the other one doesn't, who cares? Who cares? So you can write it down, f minus 1, and I put here like this, f minus 1 of f of x naught minus epsilon, and this is f of x naught plus epsilon intersection with b, with f of b is empty set. With b. With b is empty set. But that set is nothing else than v, and you just simply take one element here, this f, that's your finite set f, and your epsilon here is here given. So we just proved the basic set, there is a set, basic set. So there is an open, weak neighborhood that does not intersect b, so that means, which implies, let me go a little up, implies that complement of B is open, weakly open, weakly open. Complement is weakly open. So in such a case, so we completed the proof, therefore S and weak must be equal to B, and we got it. So I should say like this, if you look at this particular proof here, that we write, of this particular step, here, you are asking yourself, maybe I change the color. Okay, this particular step here, when we have a point and we take, let's say, we take the B, set B to be a closed convex, and A is an additional point, you can actually repeat the same argument with respect to any closed convex set. There is no need to repeat this whole proof, because this would be exactly the same. So maybe I should write corollary, maybe put it like that. This is the last part of the proof that plays the role. So I put it like this, like a continue here, and I put here like a corollary. Notice that by a similar argument as presented above, let's not corollary, that's a remark. Okay, presented above, we can show that a convex set in a Banach space convex set in a Banach space is weakly closed if and only if it is closed. In the strong topology, and that means the closed convex sets are the same. Those are the same in weak and the strong topology. They are the same. They are the same. I think we're running out of space, so maybe I finish this segment here, and I will do the proof of this one. Formulate this corollary like a properly. This is more like a remark. This is like a remark, and in the next segment I will prove that the convex sets are that their, let's say, their closedness in their closed, if and only weakly closed, if they are strong. I will prove it in the next segment. I will also consider linear operators, and we will show that a linear operator from one Banach space to another Banach space is continuous if and only if it is weakly continuous, and this will be maybe the additional observation for this particular segment that we need actually to discuss. So let me conclude in this moment this part, and let me edit it, remove some parts that I had, let's say, that I showed my inability to deal with the technical problem. So okay, it will be basically done in a moment.